La 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 la. Welcome, ladies and gentlemen. Today we are looking at sigma notation and the nth term, so we're going to be approximating, well, actually exactly aiding our nth term using, our previous tactics of recognizing patterns and whatnot. And we're going to be able to rewrite a sum of a series, right, as this new notation, all right, is the idea. So first of all, let's talk about what sigma notation is. You may have seen it before. I believe if you have been with me and you're in this course now that you have. And sigma notation looks like this. So it's, all right. Well, I guess I could say A to B maybe. They use 1 to k. That's fine. And then of some value of n. So this is what sigma notation looks like. So this n equals 1 here is the starting value for n. K is the stopping value, so we'll go from 1 to k. So if k is 10, I'm talking about the first 10 terms in a series. And then a sub n is just whatever expression I have for my nth term. And the variable n, by the way, is referred to as the index of summation. That might be a better title, Harry Potter and the Index of Summation. That sounds better, a little fancier.
Yeah, Harry Potter and the nth term sounds more like after defeating Lord Voldemort, he got blindsided by a mask.
So what this would mean is a sub 1 plus a sub 2 plus a sub 3 plus all the way to whatever my case term is, a sub k. All right, so that's what that means. So this is the Greek letter sigma. You've seen lowercase sigma before when we've done standard deviation. Capital sigma looks kind of like this weird E sort of thing. Actually, it almost looks like it would be some sort of Space Invaders ship, right? Like, like, doesn't it? I think that'd be pretty good. No? It'd make me almost want to, like, in Galaga, get one of my ships abducted, only to, like, rescue it later, so then I've got, like, the double ship side by side, so I can, like, shoot twice as many bullets. Anybody? Oh, yeah, that's what I'm talking about. Actually, now that I think about it, I think I might have used the sigma symbol when I was programming a Galaga-type game on my graphing calculator back in high school. I didn't get very far with it, but that's what I was planning on using.
Program video games in your calculator?
Yeah, graphing calculators have a program button. Yeah, you got to learn to program a little bit, but I wasn't that good at it, and I probably still am not. And the way you would read this, by the way, if you were reading this whole thing, here's my little speech bubble, I guess. You would say this as the summation of n equals 1 to k of a sub n. All right?
Oh my God.
This is my speech bubble, like, like a cartoon. I don't know. Because that's how you'd say this. I don't know, as opposed to like Garfield's thought bubble, which I always found amusing and very insightful that animals don't speak out loud in that universe, but you can clearly see that Garfield's thinking things, though.
And they can hear his thoughts.
Yes. Yeah. I guess you have to, like, just accept that fact that you, as the viewer, are able to perceive the thoughts of animals in that universe. Which I suppose is one... Yes, but I suppose that's one step greater than Dr. Dolittle, where he could just hear and understand what animals were saying. But to be an animal telepath, I mean, that's better than horse whispering, right? I don't know. If you could be an animal telepath, I don't know. I think that'd be pretty cool. So here we go. So there's all of the notation, all right, the way of writing things. So let's actually do an example. Here we are. Evaluate, I guess I'll call it. And by the way, I tried very hard to do this accurately. So this is the kind of the upper and lower bars on this symbol are parallel. So don't do this. It's not like little sideways mountains. All right. I don't know. I just try to be specific. So let's find the sum of n equals 1 to 4 of the formula 2n, let's do plus 3. So the sum of n equals 1 to 4 of 2n plus 3. So what does this actually mean? It means I'm figuring out what is 2 times 1 plus 3, and then I'm adding to that 2 times 2 plus 3, and I'm adding to that 2 times 3 plus 3, and then 2 times 4 plus 3. Yep. So the sigma symbol S is referring to sum. I'm adding up all of these values when I plug in different numbers for n. Okay? It turns out, I don't think we'll ever use it in this class, but there's also this capital pi symbol. If I have pi equals n equals 1 to 4 of n, that would be the product of 1 times 2 times 3 times 4. And actually, in this case, that would be equivalent to n 4 factorial is what this would be equivalent to there. So a little other thing to notice: capital P pi for product, capital S sigma for sum. All right, so a little parallel thought there, just so you understand the symbol a little bit more. So let's figure this out. So 2 times 1 to 5 plus 7 plus 9 plus 11. Right, so this would be my actual series. Right, that's a sub 1, a sub 2, a sub 3, a sub 4. And then I just add them up. 12 plus 9, 21 plus 11, 32. Right? So that's the idea of how to use this. All right? I guess I'll show this to you. I'll start this up here, get this warming up. So let's do one more. And we'll do find sigma, the sum of n equals 3 to 6 of, oh, I just started up the wrong thing. Oh, well. And so n equals 3 to 6 of, and let me give you a nice little function. What if I have 3 to the n, or 3 times n to the second? Let's do. Let's figure out what that is equal to. Let's see, this is what I meant to start up. So to evaluate this, we'll plug in, we're starting at 3 this time, so I just want to point out that the starting value doesn't have to be 1. I think technically it can even be negative, but the assumption here is that the values of n are always increasing by 1. All right, so 3, 4, 5, 6 is what that would be. So this would be 3 times 3 squared plus 3 times 4 squared plus 3 times 5 squared plus 3 times 6 squared, right? And we can calculate that by hand, but I want to just point out that there is also a function on graphing calculators, which I know you won't always have. But if I hit math and I scroll down, wow, it can calculate a function's max and min there. That's interesting. The derivative, the integral, those are calculus concepts. I find this summation function. It looks like it's 0 will be the shortcut to it. And actually, if you have your calculator in kind of like math font style rather than classic mode, you can kind of enter this here. So I'll do x is my variable. X starts at 3 and goes to 6. And then I plug in what my function is, 3x squared. And I believe if I just hit enter, it'll just do that for me, which is kind of a cool deal, if you ask me. But we're not really going to be using calculators, but if you used it as a check or something like that, I'd be fine. Because we're going to be kind of more curious about the relationships of everything here. So let's see, 3 times 9 is 27, plus 3 times 16, 30, plus 18, 48, plus 3 times 25 is 75, and 3 times 36, 90, plus 18, 108. And does that add up to 258? I hope so. I think so. Let's see, 68 plus 7, 75, 150. Yep, it adds up. So I just want to point out, calculators can also do this stuff. Kind of interesting, right? So evaluating those isn't that difficult. I think it's a little bit more interesting trying to rewrite something in sigma notation. So let's do this. Express in sigma notation. This is a little bit more amusing, I find. So 15 plus 24 plus 35 plus 48 plus ... all the way to 143. So this is where our pattern recognition skills will be helpful. Basically, the first thing I should do is find out what is my nth term. All right. So let's try to figure that out. Now, looking at this pattern, there's not a set difference between these. There's also not a set sum between these, so this is neither arithmetic nor geometric. And it seems to be growing a little bit quickly. Does anyone have any insight on what this pattern might be? Okay, so it's the sums of consecutive odd numbers. Plus 9. Let's see, let me get a better yellow there. So you're saying adding 9, adding 11, adding 13, something like that. Does anyone know how I could more easily... Yeah, squares go up like that. I don't know if you remember back in the days of graphing parabolas, but I said start at the vertex, go up 1 over 1, up 3 over 1, up 5 over 1, up 7 over 1, up 9 over 1. And the rises in the quote-unquote slope of a parabola happen to be consecutive odd numbers. So it turns out this pattern should somehow relate to squares. So let's just start writing down squares and figure out where does this fit. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 36, 49, 64, 81, 100. What minus 1? What are you seeing?
16 minus 1 is 15, 25 minus 1 is 24.
Okay.
44 minus 1 is 143.
Yeah, so it appears as though it is 1 less than a perfect square. But now we've got to figure out if n equals 1 for my starting value, which I guess it doesn't have to. Well, actually, there's 2 ways we could write this. Let's do it. So this would be, so if n equals 1, 4 squared was 16, so n plus 3 all squared would give me the 16 minus 1. Let's verify that that works for 24. So if n equals 2, 2 plus 3 is 5, 5 squared is 25, minus 1 is 24. So that seems to work. Now it turns out, like I said earlier, we don't technically have to start with n equals 1. I could start with n equals 3 or 4 or 5, if that's helpful. But let's use this first, and then we'll write this a second way, is what we'll end up doing. Let's see. So we'll do this 2 separate ways here. So to write this in terms of sigma, man, my sigmas are getting uglier over time. So we're going to start with n equals 1, and we're using this pattern. How do we figure that out?
Because 143 is 1 less than 12 squared, and we're adding 3 to each n.
Right. Now could we generalize that approach? Because I think that's a little bit tricky, like what happens when this formula is crazy, which it kind of is a little crazy right here. But yeah, the issue is this. First of all, this list didn't go on forever. If it did, I actually can have infinity be part of that sigma notation. But I want to figure out what n term is this, what value of n is that, and what you can actually do is just set 143 equal to this formula and solve for n. So n plus 3 all squared minus 1 equals 143. So n plus 3 all squared equals 144. Root, we'll get plus or minus 12, technically, but I think we're only considering the positive value here. And then n equals 12 minus 3 is 9. So in order to find out where my stopping value is, that's what you can end up doing, is setting the last term equal to your formula and solving for n algebraically, yeah. So, yeah, let's consider, what if I called my nth term this?
That's what I would have done.
Yeah.
You would start with n equals 4.
N equals 4, and then we
Go to 12.
So n squared minus 1. So n starts at 4, you're saying? And how could I prove that? How could I know that? I could plug 15 equal to this. 15 equals n squared minus 1. Add 1 to both sides, root. I get n equals 4. And now is this going to stop at 9? No, it's going to stop at 12 here. And the way I would find that is by setting the 143 equal to n squared minus 1. Add 1 to both sides is 144. Root is 12. All right, so I want to point out there's actually multiple answers to some of these depending on what you perceive as the easiest starting value for n. Okay? But it's all about figuring out what is my pattern, what is my nth term, and then figuring out what would the starting number be, what would the ending number be based on those, yes. Yes, I would. And clearly it would be a little bit tricky if I was doing a multiple choice. You'd have to, maybe there's multiple real answers to it, and maybe I even take those into account, but only one of them actually works, or I'd maybe make some sort of error on one where it'd be off for k value or something like that. And I do want to point out that notice 9 minus 8, 9 minus 1 is 8, and 12 minus 4 is 8. So the difference between k and my n's starting value is always going to be the number of terms that I have. All right, so that is consistent between both of those. So let's do one more. I think I'll fit it up here. Sigma notation. Yes. Example. Actually, I'm tempted to write example this way because I think. Am I right? Am I right, people? Although technically sigma is the letter S, but I think we all agree it looks a lot like an E. I'm tempted to make some sort of mathematical gang sign with my hands to make it look like an E, but I don't know. I don't know if that works. Yeah, it's difficult. Just east side maybe rather than sigma. Yeah. Yeah, don't flash mathematical gang signs around in bad neighborhoods maybe.
Maybe if you flash them in the right way, you can use dim-witted gangs.
Yes, maybe. I hope there aren't any mathematical gangs here either. The mathematical community is an international one where all of us share. It's wonderful. Okay. I'll just stop at this. All right, so we've actually got 5 terms. Whoa, slow down, friend. So let's figure out what is our nth term. And once again, I want to point out, notice if these fractions were reduced, it would probably be really hard to notice the pattern. That would stink. So be aware of that. So let's look at just the numerators. I like to break it up. So 2, 4, 6, 8, 10, that sounds like evens, so I'm going to call that 2n. At least for when n equals 1, that seems to be the case. Right? 2, 6, 24, 120, 720. Yeah, those happen to be factorial numbers. And just to verify, does anyone know what 0 factorial is defined as? It's defined as 1. Not necessarily the most intuitive thing. It's just, I think it has more to do with the fact that it works really well with our combinatorics formulas, where you'd end up with like n minus r factorial in a denominator, and then you end up like if n and r are the same value, you'd get a 0 factorial in a denominator, and if 0 factorial was 0, it's in the denominator, and it ruins your probability because it'd be undefined. Right. So I think they defined it as equaling 1, and it ends up everything works out really great. So sometimes the discovery of mathematics, like you come to a crossroads where you have to almost like decide what is this going to mean to us, and you'll choose the one that maybe makes the most sense, is what ends up happening, yeah. So yeah, those are all factorial numbers. So 2 is what factorial, though? 2 factorial. 6 is 3 factorial. 24 is 4 factorial. So it looks like it's 1 more than this n, whatever that n happens to be. But now there's one more issue.
It fluctuates.
The signs are alternating. Well, I'm going to deal with the signs at the very end. Does anyone have an idea of how we could fix that? Is it convergent? So I don't think the limit would exist because of the alternating nature of it. But how could I simulate alternating signs? Put in a negative, so just, oh, now it's just negative all the time. Where have we seen alternating signs before? Everywhere. What if I multiply by -1? That would mess things up. We would get alternating signs, but they would be alternating only every other term, and then we'd have imaginary terms.
-1 to the n plus 1 power.
-1 to the n plus 1 power? Well, think about it. If negative 1 is raised to an even exponent, it's positive. And if it's raised to an odd exponent, it's negative. So there would be our alternating signs. And if n is equal to 1 for my first term,
N plus 1.
yeah, it looks like I'd have to do n plus 1, or technically n minus 1.
Oh.
Or n plus or minus any odd number, as a matter of fact, would work, and it wouldn't matter.
Except if it was negative. If it was negative, then that would
Well, it would reciprocate it, but then the sign would still be, yeah, somewhat amusing. So n plus 1th power. Let me shift things over here a little bit. Negative 1 to the n plus 1th power. And that's how I simulate.
The n plus 1 power in front of the numerator, not behind it. I just did that because I didn't want to erase it.
Okay, yeah, that's fine. Yeah, you could fit it over here or whatever. Yep. So, okay, so there's my nth term, assuming n starts at 1, right? So let's write this in sigma notation. So the sum of n equals 1 of this pattern. I wonder how well your calculator would handle this. I imagine it would do just fine. And now the question is, where is my stopping value? Actually, I might even have some multiple choice questions that are specifically like this, and then I'll just have like a blank here, and I'd say what goes in the blank.
5.
So it requires 5.
Yeah.
2 times 5 is 10. Negative 1 to the 6th power is positive. 5 plus 1 is 6. 6 factorial is 720. Yeah. Now that's what is kind of nice. Since I defined this pattern in pieces, I technically could have just solved this by doing like a little piecemeal thing of when is 10 equal to 2n?
It's going to be positive.
And n equals 5. And yeah, and it is positive. So it all works out. Oh, the sum? Oh, okay. Now, we could have n start at 2. Let's do that. Let's see. Although I think we'd end up with another offset because not all of our n's were plus 1. But yeah, let's define that formula. Let's do it a separate way. So what if a sub n was equal to, you'd say negative 1 to the n factorial, and 2n minus 1? Two n minus 1 in this current form would be an odd number. 2 parentheses n minus 1 would work. Okay, I agree. So let's figure out what's sigma notation for this. Okay, I like it. So it's definitely worth seeing multiple setups for these. Right, and then it's just a matter of preference. Let me open up the calculator. I'm interested to see how well it could handle this. So let's see, it was the 0th one there, 0th menu. So x equals, I'm going to do this one, 2 to the 6th of, and let's see if I can plug this in proper, negative 1 to the nth, or x in this case, right, multiplied by 2 times x minus 1. All right, so there's my numerator. It looks like I probably would have to add some parentheses to this, another set, huh? This big parentheses is the parentheses of like the whole sigma applying to that. Let's see, and one more. There we go. Second, insert parentheses. There we go. Over. I find that the graphing calculator emulator here, sometimes my over keys are miscalculated. So it's difficult. It's twitchy. Divided by, and I want n factorial. So x, and how do I simulate factorial? Does anyone know? Turns out, math probability menu, there's actually a factorial symbol there. I could also multiply it by some random integer, apparently. So let's hit enter on this, and I get 0.53055 blah blah repeating. So it appears as though this works out. Oh, wrong thing here. Blah, paste. Right, and I mean, finding that sum by either doing that or maybe in this case it would have just been easier to plug in those fractions since it was such a short list. Yeah, I mean, it's easier finding the actual sum in this case than I think it was finding the formula. Let me do second entry, and then in this case, I could change my values of k and find the sum of the first 10 terms and different things like that. Let's see. Over. So I think I could even do, like, how many terms would that be?
9.
That would be 8 terms, 10 minus 2.
9. Yeah, it would be 9.
It would be 9. It would be 9, yeah, so I did have an error previously in this video. Wow, It appears as though this could be converging. It could, what if it converges at a half or something like that?
Well, because you have alternating signs, so if
Yeah.
it was 1, and then subtracted a lot, and now you've got super small fractions.
Yeah.
Can you do it to infinity?
We'd have to take the limit of the sum, which is actually a calculus concept we'll do later. But I think we're done for today. So, goodbye, Internet.